we're going to prove, using the sandwich theorem, that the limit as x approaches 0 of sine x over x is 1. And I have this lovely picture over here that would appear to have absolutely nothing to do with the graph of sine x over x. Would you pretty much agree with that? We just looked at the graph of sine x over x. Doesn't look like this has anything to do with it. It's like part of a circle. In fact, we'll call this the unit circle we got going around there. And then I got like some triangles drawn in there. A couple of them are like inside the circle. And then we got this triangle that's outside the circle and all that fun stuff. It's good stuff, right? You're all very excited by this, I can tell. So let's label a few things on our picture. First off, we are talking about finding the limit as x approaches 0 of sine of x over x. So based on that, what should the angle right here perhaps be? What do you want to call that angle?
Angle x.
That sounds like a great name for that angle. Angle x. I love it. Makes sense since we got the sine of x, right? X is clearly an angle. Cool. All right, if that is x, is there anything else that we can label on this picture based on the fact that I told you this is a unit circle, right? We know what a unit circle is, yes?
Yes.
What else can we label?
The 90 minus x on the other leg of the triangle.
Okay, so this one is 90 minus x, you're saying? So maybe we'll make that a right angle here. In fact, on both sides, we can make that a right angle. All right, 90 minus x for this one. That is true. That is 100% correct. We're not going to need that angle, so I'm not going to label that because my picture is going to get really convoluted in a second. But you are correct. That angle should be 90 minus x. What other things based on this being a unit circle could we know? For example, what is this length of this hypotenuse of this little right triangle? That'll be what? R. Yeah, it ought to be 1. All right, that's a good start. Well, let's see. This point right up here ought to be what? What should that point be? How does the points on a unit circle work? The x coordinate is always cosine, and the y coordinate is always sine. I'm going to write this out here. This is the point cosine x comma sine x. Which, does that tell us anything about this? It should tell us what that length is, right? That length ought to be cosine x, right? Cosine of this angle, x, ought to be adjacent over hypotenuse. And what should this height be up here?
Sine x.
Should be sine x. Yep, right? Okay, that is not all that we need, but that's going to be good enough for right now. So the first thing I want us to do is take a look. Oh, that didn't work. Take a look at, oh, that looks horrible. Let's try and draw this better. Take a look at this triangle right here. Somebody help me out and tell me, what is the area of that triangle? We should know that base. That base should be what?
1/2 sine x would be the thing because the base would be 1.
Right, the base would be 1. So the area of the triangle in red, so I'm going to see here. I'm going to write this here. It should be 1/2 the base times the height. So 1/2 of 1 times sine x. All right, cool. Next thing I want you to do is take just a second here And here we have a sector of the circle. Think about for a second what you think the area of that sector of that circle should be. Any ideas on what that should be? All right, this is the sector of a circle. What's the area of the full circle?
Pi squared.
Yeah, the entire circle ought to be pi times the radius squared. Well, what's our radius?
1.
Yep, so this should just be pi times 1 squared, or just pi for the entire circle, right? But all we want is a piece of the circle. So how much of that circle do we have? How many radians do we have?
X.
We have x radians out of how many total?
2 pi.
Right, x out of 2 pi radians. So if we take the fraction that we have and multiply it by the area of the full circle, that ought to give us the area of the sector, which looks like it should be what? Just 1/2 x if we cancel out those pi's. Would you guys agree with that?
Yes.
Yes.
Wonderful. All right. Next thing I want you to find for me is, it's the same color. I tried to change that to green. The area of this triangle, and I'm gonna let you know that this right here is a right angle. What's the area of that bigger triangle going to be? Well, we need to know, we got the base, right? We need to know the height. What's the height of that triangle going to be?
1.
It looks like it should be, right? But it is not necessarily going to be 1 because we don't know that this is a 45-degree angle, right? And we could have drawn this so that maybe it was like this or up higher like this. We can't be guaranteed that's a 45-degree angle to make that height 1. But there should be a specific trig function that it's equal to. What trig function should that equal?
Tangent?
It should be tangent, exactly. Why should it be tangent?
Because it's sine over cosine.
How did you get that it was sine over cosine? There's one way you could get it. I'm just curious how you got it. And then there's another reason it could be tangent. There's 2 good reasons it's tangent. So how did you determine that it's sine over cosine?
Isn't that like the definition of tangent?
Well, yeah, but like, where did you get sine over cosine from?
Couldn't tell you.
Okay. So the 2 different ways that we can see that that height is tangent to x is, 1, this little right triangle in here is a similar triangle to this big right triangle out here. Right? Remember, similar triangles, if they have an angle in common and then another angle in common, right? So x is the same for both of them and they both have a right angle. That means that they're similar triangles, and the ratio of the height to the base should be equal to the ratio of the height to the base. So sine x over cosine x needs to equal that height over 1. Well, sine over cosine is tangent, so that height has to be tangent. Alternatively, we could have just said that the tangent of this angle x ought to be this opposite side over the adjacent side, which would have been tangent x equals this height over 1 also. So either way, it'll get tangent x as that height. Everybody okay with that?
Yes.
All right. And what does that make that area? Area should just be 1/2 tangent x. You all agree there? 1/2 base times height.
Yes.
All right, cool. All right, we've done all the hard work. Now, what can you tell me about the little red triangle in comparison to the sector of the circle? Which one's bigger? So red triangle's area bigger, or is the area of the sector of the circle bigger?
The sector is bigger.
Sector is bigger. So we could say that 1/2 sine x is always less than or equal to 1/2 x. And what about the sector of the circle in this triangle that lies outside of it? Same thing, right? The sector of the circle is less than the tangent one. Yeah? Everybody agree with this inequality? This inequality must be true.
Yes.
All right, cool. Now we are on track to figure out why the limit as x approaches 0 of sine x over x is 1. All we have to do is turn this thing in the middle into what?
Sine x over x.
Sine x over x. So I think the first and easiest way to do any of that is if we just multiply everything by 2, just to simplify stuff. We get sine x is less than or equal to x is less than or equal to, and I'm going to rewrite tangent x as sine x over cosine x. And then what? What else do we need inside the middle here? We need to get a
Sine.
We need to get a sign in there. So let's, and we need it to be on the opposite part of a fraction of the x. So why don't we start off by just dividing everything in each one of these by sine x, and then we'll at least have the reciprocal of what we need. And then we could take the reciprocal of it, right? So if I divide everything by sine x, that's okay to do, right? Do any inequality signs need to flip if we divide by sine x?
No.
No, why not? Because sine x can be negative, right? But you're right, they don't need to flip. Why not?
There are no negatives.
Well, there are definitely, there's definitely values of sine x that are negative, but all of our values of x are in the first quadrant here to make these triangles. And so the sine of x in the first quadrant is always positive, right? We know that first quadrant sine is positive, second quadrant sine is positive, third and fourth it's negative, right? Should know that, I hope. So what does this give us? It gives us 1 is less than or equal to x over sine x is less than or equal to 1 over cosine x. And now all we have to do to get sine x over x in the middle is take a reciprocal. And that should be easy enough. The reciprocal of x over sine x is sine x over x. What's the reciprocal of 1? It's just 1. And the reciprocal of 1 over cosine should just be cosine. What happens when you take the reciprocal of every piece of an inequality?
You flip the signs.
You flip the signs. If you didn't already know that, you should know that now. Anytime you take the reciprocal of everything in an inequality, you got to flip the signs. So that's okay, because now we just have this other true inequality, right? That in the first quadrant here, at least, sine x over x is greater than or equal to cosine x, and it's less than or equal to 1. And so all we'll need to do is find the limit as x approaches 0 of 1, which is what?
1.
1. And we'll need to find the limit as x approaches 0 of cosine x, which is the cosine of 0, which is 1. And that tells us that by the sandwich theorem or the squeeze theorem, this limit is also equal to 1. Everybody good with that?
Yes.
Yes.
All right, spectacular. Now, this is a limit that you will want to commit to your memory because it's a limit that will pop up quite often that you'll need to use. I'm going to give you a bunch more of ones that you need to know today. By the end of the day, we're going to start with one more of them right now. And I'm going to do that by looking at this inequality that we had as we were going partway through. Right? Didn't we have that inequality right here?
Yeah.
Yeah, that's the inequality I just wrote here. What's the limit as x approaches 0 of 1? We already did that, right? It is
1.
1. And what's the limit as x approaches 0 of 1 over cosine x? That would be 1 over the cosine of 0, which is 1. What does that tell you about the limit as x approaches 0 of x over sine x? It ought to also equal
1.
1. So there's another one that you're going to want to know and have memorized. That the limit as x approaches 0 of x over sine x and the limit as x approaches 0 of sine x over x are both 1. Everybody good with that?
Yes.
Spectacular. All right, commit those two to memory. I expect that you have them memorized now. And be careful, remember that it has to be as x approaches 0 for both of them. Because at some point down the road, I might end up giving you a limit of one of these two things, but x isn't approaching 0. And so then you cannot apply this rule. It has to be as x approaches 0. All right, so let's take a look at one that is slightly different. The limit as x approaches 0 of sine of 5x over x. Very similar to the last one, right? What should we do? Should we draw a unit circle and draw all those millions of triangles and sectors of circles and call the angle 5x and go through that whole process again?
No.
Yeah, that sounds awful, doesn't it? We don't want to do that again. What do you think we can do then? Any thoughts?
Use the inequality we found on the last question.
Well, the problem with that inequality, though, is that it's just got sine of x, not sine of 5x. I can't just put a 5x inside the argument of a sine, right? That's like breaking rules of math. What do we notice, though, perhaps, about this limit? That the sine of the angle that we've got is also in the denominator, but we don't have that here, right? The angle that we're given is not in the denominator. So I'm going to suggest that we start off by putting that angle of 5x also in the denominator. And how can I do that?
Multiply both sides by 5.
Yeah, multiply the top of this by 5 and the bottom of it by 5 as well. And now I have something very, very similar to what I had before, right? Except instead of it being sine of x over x, it's sine of 5x over 5x. And I've also got this 5 out in front that's a coefficient. Well, we got a rule for coefficients, right? What can I do with a coefficient in a limit?
You can put it in front of the limit.
Put it in front of the limit. So I could then say that this is equal to 5 times the limit as x approaches 0 of sine 5x over 5x. What do you think the limit as x approaches 0 of sine of 5x over 5x is?
One.
Yeah, one would think that it's 1, or maybe somebody might think it's 5, right? Those are kind of the two things we might think of. It's definitely 1, but we need to prove that it's 1. Anybody see a good way to prove that that's 1? That this piece of it here, without the 5, is 1, without going through a long and complicated process? We've done a couple of limits using this same method, except they looked very different.
Are we going to use squeeze for this one too?
Nah, that's a lot of work. I don't want to do that much work. I want to do something much easier.
Substitute the 5x for u.
That sounds like a great plan. Let's let u equal 5x. We've done some limits where we did u substitutions, right? So we're going to let u equal 5x. All right, well, that's cool. That's going to give me sine u over u, right? As x approaches 0. So I don't want x approaching 0. I want it to be u approaching something, right? So what happens to u as x approaches 0? As x approaches 0, u approaches
0.
also 0. Convenient. So this limit can become 5 times the limit as u approaches 0 of sine of u over u, which is, we have a constant out in front, 5 times, what's that limit right there?
1.
Okay, it's 1. We just proved that a minute ago. So our result is 5. Good or no?
Good.
All right. This whole idea of doing this u substitution is super convenient to simplify pretty much any one of these about to be very unpleasant looking limits into something very simple to deal with. And I won't force you to always write out the u substitution, because we're going to get to the point where we recognize that as long as the limit as x approaches 0 and it's the sine of something up here in the numerator, and that same thing is in the denominator, it's always going to come out to be 1. But we'll do one more with the substitution just to kind of illustrate that. So here's another one. This one looks more complicated, doesn't it? And I always keep forgetting this. Let's make that y approaches 0. The limit is y approaches 0. The sine cubed 4y over y cubed. So we should be able to use the different properties of limits that we know and the known limit that the limit as y approaches 0 of sine y over y is equal to 1 to simplify this down into a workable limit. Any thoughts on the first step?
You could pull the exponent out.
All right, yeah, they're both being raised to the third power, right? So I could say, and I'm going to do this, you don't need to do this in 2 steps, but I'm going to do it in 2 steps. Sine 4y over y cubed, right? We're cubing the numerator and we're cubing the denominator, which means we've effectively cubed the entire fraction. Now, in a minute, we know we have a rule where we can take the cube that's around the entire argument of the limit and pull it outside the limit, which we'll do in just a second. But we also need to be able to simplify the sine 4y over y down. And what do I need to put in the denominator in order to do that?
4.
For y.
4, right?
4.
And what do I need to then put in my numerator?
4.
Right. And so what can we do with this 4? That is a constant out in front.
Bring the 4 as well as the cubed in front of the limit.
Perfect, yeah. So we can't forget that this 4 is inside parentheses being cubed. So we're going to have 4 cubed times the limit as y approaches 0 of sine of 4y over 4y. And that sine 4y over 4y was all cubed. So I can bring it outside all of this and say that it is now all being cubed. Everybody good with moving from that step to this one?
Yeah.
All right. And what's 4 cubed? 4 cubed is 64. And what's the limit at 1 to 0 of sine 4y over 4y?
1.
Yeah, that's 1. And we could write out the u substitution with u equal to 4y. And then instead of y approaching 0, u would be approaching 0. But I think we probably are good if we don't necessarily write it out. So we end up with 64 times 1 cubed, which is 64. Good or no? All right. Spectacular. Let's do another one. You guys want to try and do this one on your own, or do you want to work through this one together still?
We got this one.
You got this one? Okay. All right. I'm going to give you guys about 2 minutes to work through this on your own. So ready, go. So what's the first thing that you probably did here that I hope that you did?
Double the exponents.
All right, so one option would be dealing with the exponents. That's actually probably not what I would do first. That's probably my second thing to go to here. First off, I think I'm going to just take this 4 in the denominator and pull it out, because that's going to make dealing with the exponents a little bit easier. So we're going to have 1/4 the limit as z approaches 0. Now I could rewrite this as sine of 3z cubed over z cubed, all being raised to the 4th. If you leave that 4 in there, and then you gotta like take a 4th root of it, which ends up making it like a square root of 2, and it's a little bit of a pain. So everybody good with that? I would deal with that constant first, pull that 1/4 out. And then what needs to be put in the denominator of our fraction?
3.
A 3, which means we also need to put a 3 in the numerator. And then that constant that's in the numerator, that 3, can be pulled out, but as it gets pulled out, it becomes 3 to the 4th power over 4. And then we've got the limit as z approaches 0 of sine of 3z cubed over 3z cubed. And that entire limit can now be raised to the power of 4. Everybody good with that or no?
Yes.
All right, and 3 to the 4th power ought to be 81. So we got 81/4 times 1 to the 4th, which will be 81/4. Good or no?
Good.
All right, cool. Let's do another one. The limit is y approaches 0 of 2y plus sine 3y all over 4y. What can we do with this, do you think? Looks a little different, right? We got a plus in here, right? That's going to change things up a little, isn't it? Any thoughts on how to
Yes.
deal with? How are we going to deal with that? Okay, we need to use some of our other limit rules. We're going to write this as the limit as y approaches 0. And I'm going to separate this into 2 different limits. By using addition. Everybody good with that or no?
Yes.
Yeah.
So if we're going to take the limit as y approaches 0 of 2y over 4y, well, that's obviously 0 over 0, but we can cancel out the y's, right? So that ought to become the limit as y approaches 0 of 2/4 or a half. And then what should I pull out of this second one?
Oh, 1/4.
1/4 of the limit as y approaches 0 sine of 3y over y. And how am I going to deal with this second limit here? What do I need to do?
Put a 3 on the top and the bottom, and then take the top 3 and put it in the front.
Perfect. All right. So what's the limit as y approaches 0 of this constant 1/2? That should be
1/2.
1/2. And then we'll do just what we were saying here. We'll pull that 3 out as a 3/4. The limit as y approaches 0 sine of 3y over 3y. Now this looks just like a limit that we know the value to be 1. So we got 1/2 plus 3/4 of 1, or what does that become? 5/4. Good or no?
Good.
All right. Let's take a look at another one. This one is very different, obviously. The limit as x approaches 0 of 1 minus cosine x over x. Any thoughts on this one?
Expand it like we did.
You mean like the previous one?
Yeah.
So, okay, so let's give that a shot. We're gonna do the limit as x approaches 0 of 1 over x minus cosine x over x, right? So let's think about this. If we plug in 0, what do we end up with on this first limit? Get 1 over 0, which is undefined. And so immediately we're at a problem here. We can't have something that's just undefined. Well, we could. It would just mean that the limit doesn't exist, but this limit does exist. And so we're going to see if we can find another way around that. That's a good idea, though. And that is a method that will often work for problems similar to this. Any other thoughts on what we could do with this? It's an indeterminate limit, right? If I plug in 0, I get 1 minus 1, which is 0, over 0. What were the different ways that we were able to deal with indeterminate limits? One was factoring, right? I don't see anything to factor.
U substitution.
Another was U substitution. But nothing in there is super like complicated. I don't think we want to use a U substitution. What were some of the other ways?
Multiplying by the conjugate.
Multiplying by the conjugate, yeah. And that normally only worked with our radicals, right? But I think I might have mentioned that sometimes with trig functions, it can be super helpful as well. So let's try that. Let's multiply by the conjugate of 1 minus cosine x to both the numerator and the denominator. So that'd be 1 plus cosine x. And what does that give us in the numerator? What's 1 minus cosine times 1 plus cosine?
Sine
X
of
plus x cosine x.
Sorry, say that again. You were all sort of talking at the same time, I think.
X plus x cosine x.
No, that's in the denominator, but in the numerator. So 1 minus cosine times the 1 plus cosine?
1 minus cosine x squared.
Yeah, 1 minus cosine squared x. And it now looks more complicated, but the good news is it's in a much better form, because what does 1 minus cosine squared x equal?
Sine x.
It equals, not sine x, but sine squared, right? And I'm going to write this out real quick. You guys should all be familiar with the Pythagorean trig identity, right? Sine squared x plus cosine squared x equals 1. So 1 minus cosine squared x ought to equal sine squared x. And that's good news because all these other ones that we've been dealing with have had sine x's in the numerator, right? And now we've got at least we got a sine x in the numerator now. So what we're going to need to do is we're going to need to separate this out a little bit. Any ideas on how we're going to separate it? No ideas? All right, I'm going to do it for you then. We're going to do sine x over x as one limit, and we're going to do the other limit as sine x over 1 plus cosine x. Because didn't we have a rule where we could separate a limit using multiplication?
Yeah.
Yes.
Yeah, and I think if I multiply this all back out, I should get sine squared x times 1 plus over x times 1 plus cosine x, right? Should be exactly the same. So what's that first limit? The limit as x approaches 0 of sine x over x.
1.
That should just be 1. And what about this other one? Well, we should probably plug in the 0 and see what we get. We get 0 over 1 plus cosine 0. What's the cosine of 0?
1.
1. So we've really just got 1 times 0, which is 0. So this limit is 0. And this is another limit that you're going to want to have memorized. The limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Good or no?
I need a bit longer to look this through.
I can leave it up there for a second. And while you're looking through it, I'm going to also let you guys know this is another one that we're not going to prove, but that is exceptionally similar. This limit is also equal to 0. And so you'll want to memorize this one as well. So both the ones I've starred on here should be ones that you memorize. Everybody good there or no?
All right, I'm good.
All right, so make sure we now got 4 that we need to have memorized, right? The limit as x approaches 0 of sine x over x, x over sine x, and then these 2 on this page. All right, let's see if we can use that rule to help us with this limit. 1 minus cosine 10x over x. What do you think we should do?
Do we multiply it by the conjugate again?
Well, we could, right? If we go through and multiply by all this conjugate stuff, we're going to get a very similar process as this. But we should be able to take a shortcut now. Because
Go
ahead.
First, we have to separate it.
No, we don't need to separate it. We should be able to just really quickly do something very similar to what we did with the sine ones to solve this one without having to go through any of the longer process that we just did.
Multiply both by 10.
Yeah, let's take the numerator and the denominator and multiply them both by 10. Because that way, at least I've got the 1 minus cosine u over u, and I can pull that 10 out into the front. And if I wanted to make that substitution where u is equal to 10x, as x approaches 0, u would be approaching 0 also, and we'd have the 10 times the limit as u approaches 0 of 1 minus cosine u over u. And we already know what this limit right here is. It is 0. And so 10 times 0 just gives us 0. Everybody okay with that or no?
Yeah.
All right. And from now on, you don't have to write out the u substitution for the cosine ones like this either. You can just know that if it's 1 minus cosine of some function over that same function, as x approaches 0, it's going to still be 0. All right, let's look at one that's a little bit more complicated. Looks a bit more complicated, yeah? What should we
Just a
do?
little bit.
Yeah, a little bit. What should we do with this? Any thoughts? This should look really familiar to you, sort of. Some part of this should look familiar, I hope. But it
U
doesn't.
equals cosine of x.
All right, if u equals cosine of x, we're going to end up with 1 minus 4u plus 6u squared minus 4u cubed plus u to the 4th, right? But if u is cosine x, that's going to put x is equal to the inverse cosine of u. And I don't know if we want an inverse cosine of u to the 4th power. That's going to sound pretty unpleasant, I think. There should be an easier way to do this one. Shouldn't have to make a substitution at all. But it doesn't sound to me like you guys know what you need to know to do this. So we're going to go over something that you should have learned in the past that would help you, that you probably have learned but just didn't recognize. What is this?
1.
That's right. Good. Okay. What is this?
Oh.
It's another couple of 1s.
3.
And what is this? This is another 1 on the outside, and 1 and 1 makes 2. And add these ones together, and add these ones together.
Oh, wait, what's that? What's this called again?
This is called Pascal's
Pascal's
triangle.
Yeah. All right.
And this is something you should be at least vaguely familiar with. Right? It's something you've probably all seen, you just maybe didn't recognize it right off the bat. And you may not even remember what is important about it. But what's important about it is this 1, 4, 6, 4, 1, at least in the context of this problem, because 1, 4, 6, 4, 1 are our coefficients. Well, what do these numbers in Pascal's triangle, they represent a lot of things, but what is one thing that the numbers in Pascal's triangle represent?
I think they represent a perfect, like, I don't know, it like represents being able to multiply it just x plus or minus coefficient x plus or minus something, like the same thing multiple times, I think.
Exactly. I'm going to use a and b. But what's a plus b to the 0 power? It's just 1, right? And what's a plus b to the 1st power? Well, it's just a plus b. The coefficient is a 1. The coefficients on both the a and the b are 1s. What about a plus b squared? Well, it's a squared plus 2ab plus b squared. 1, 2, 1. 1, 2, 1. You should know a plus b cubed, one would hope, a cubed plus 3a squared b plus 3ab squared plus b cubed, 1, 3, 3, 1. Well, for each one of these, each row in Pascal's triangle is the expansion of a binomial to that power. Okay. So I have 1, 4, 6, 4, 1, just like I have 1, 4, 6, 4, 1 here, which tells me that this is the perfect square of a plus b, or maybe a minus b. In fact, this one is a minus b because of the minus signs that are in there. We'll talk about that in a second. To the fourth power. So this ought to be a minus b to the fourth, with a equal to 1 and b equal to cosine x. So we'll note that this could be plus or minus on here for each of these, right? If this was a minus, then this second one here becomes a minus sign. If this was a minus, then the second one becomes a minus sign, then it's a plus, then it's a minus. So I'm going to note that for a minus b to the nth power, whichever power we're at, the signs will alternate. Everybody okay with that or no?
Yes.
All right, cool. So we should be able to rewrite this as the limit as x approaches 0. Hold on 1 second. Sorry, this should become the limit as x approaches 0 of 1 minus cosine x to the fourth over x to the fourth. And now we can use our same rules that we had before. Just turn this into 1 minus cosine x over x and raise the whole thing to the fourth power, giving us 0 to the fourth, or 0. Everybody good with that?
Yeah.
Perfect. All right, let's take a look at another one. Sorry, give me 1 second again. Okay, sorry about that. So here we got the limit as y approaches 0 of sine 4y over sine 10y. Any thoughts on this one? It's different than the cosine one, obviously. Any thoughts on that one? No thoughts? All right, let's do this. The limit as y approaches 0 of sine of 4y over 1 times what? I want to write that one separately.
1
The
over
limit of
10y.
Yeah, 1 over sine 10y. And I heard somebody saying a limit of 1 over sine 10y. That's true. It could be the limit of 1 over sine 10y. But for right now, we're going to keep them all within the same limit, and we'll go back later on and separate them.
Yeah,
What would I
side,
need in? Sorry, go ahead.
side question. Every time you write the equation, do you have to constantly write limit y 0, or is okay if you
Yes.
just put it aside?
Nope, you have to write it every single time until you start evaluating.
Oh,
So this sine 4y over 1, in order for that to be a limit that we could deal with easily, what would we need to put in the denominator?
A 4y.
That's right, a 4y is, so we'll put that 4y down there. I'm not going to put anything else anywhere else yet. What could I put in the numerator of the other one to make it easier to deal with?
A 10y.
A 10y. All right, cool. Now we're going to cancel all this stuff out. So first off, I put a y in the numerator and I put a y in the denominator. Am I good there? Do I need to do anything else to anything else anywhere? For just the y and the y?
No.
Nah, should be good there. I did put a 10 in the numerator, but I didn't put a 10 in the denominator for 4. So maybe I need to put a 10 down here. And then I put a 4 in the denominator, so I probably need to put a 4 up here also. Yeah. And now this should look very nice. All I have to do is separate it into two different limits. The first one will be the sine 4y over 4y, and I'll put a 4 out in front. And the second one will be 1/10. I'll pull that 1/10 out. The limit is y approaches 0 of 10y over sine 10y. And what do we get? We get 4 times 1 times 1/10 times 1. And that ought to just be 4/10 or 2/5. Good or no?
oh wait, but for the numerator, you're multiplying one part by 4y and then just multiplying the other part by 4, though.
No, I multiplied by the y over here.
Oh, yeah, all right.
The entire thing that I put into the numerator of this was 4 times 10 times y, right? It was 40y, and everything I put into the denominator equaled out to 4 times y times 10, also 40y. So it doesn't matter which fraction it's in, right? Two fractions multiplied together, you're just multiplying straight across in the numerator and the denominator. So as long as it all multiplies out to be the same thing in the numerator and denominator, it's all good. Any other questions on that one? All right. Before we do this one, let's do something else. Let's do a limit as x approaches 0 of the tangent of 2x, actually the tangent of x over x. Any thoughts on what we might want to do with this one?
Split the tan x into sine x over cosine x.
Perfect. So we'll have a limit as x approaches 0 of sine x over x cosine x. Everybody good with that?
Yeah.
Right, the sine x and the cosine x just drops into the denominator. So how could I split this one up into two different limits?
Sine
What
x
the
over
limit?
x.
Yeah, sine x over x, that's one that I know, right? And what's the other one then going to be?
1 over cosine x.
Or cosine x, perfect. And the limit as x approaches 0 of sine x over x is 1. And what about this one? This ought to be 1 over the cosine of 0, which is 1. Good or no?
All good.
So I'm going to go to another new page here. This limit, the limit as x approaches 0 of tangent x over x is equal to 1. You should memorize that, and you should also memorize this one, which we didn't prove, but can be proven in essentially the exact same way. X over tangent x, that limit as x approaches 0 is also 1. So those are the 6 trig limits that you should memorize. Sine x over x over sine x, tangent x over x, and x over tangent x are all 1. And then the limit as x approaches 0 of 1 minus cosine x over x and cosine x minus 1 over x are both 0. So you're going to need all of those for tonight's homework.
Oh, wait. How did you get to limit tan x over x equals 1?
Did it right here?
Yeah, all
Yeah.
right.
And over cosine. So we separated that into sine x times over.
Oh, yeah, okay.
All right. So let's do one more. Looks like we got time for one more. Quit for today. Limit as x approaches 0 of tangent 3x over tangent 4x. It should be very similar to what we were doing with the one that was sine 4x over sine 10x, I think, after we split this up.
Tangent of 3x over 1 times 1 over tan 4x.
Perfect. And turn this first one into one that we can deal with. We need a 3x in the denominator. And to turn the second one into something we can deal with, we need a 4x in the numerator. X's cancel each other out, so that's good. But we put a 3 in the denominator, which means we need a 3 in the numerator. And we put a 4 in the numerator, which means we need a 4 in the denominator. Everybody good there? And the coefficients that I can pull out are the 3 in the numerator and the denominator. Pull that out 3/4 times left is x 0 and 3x over 3x times the limit of x approaches 0 of 4x over tangent 4x. And what should each of these limits be? First one, 1, and the second one can also be 1. Pretty good there or no?
Yeah.